All right, so one thing that you did not talk about last year was the topic of sequences in series. Okay, this is very new to you. So first of all, I would like you and your pod to take a few seconds and discuss what you think a sequence is, mathematically. 1, 2, 3, go. All right, pod 4, what do you have for us here?
Does the sequence involve order of the way things are arranged?
Okay, the way things are arranged.
Yeah.
Okay, pod 2, what do you have to add to that?
You said it was basically just like a pattern.
A pattern, okay, a pattern in a certain order. And since we're in math class, this certain order or pattern would involve what?
Numbers and variables.
Numbers. Numbers is what we are going to focus on. All right, so a sequence is an ordered progression of numbers. Numbers that have a pattern. And then we say that the domain of the set of the sequence is the set of positive numbers. Oh, positive integers, excuse me. Henry, what's the first positive integer?
1.
Thank you. The domain of a sequence is the set of positive integers. Henry said our first positive integer is 1. So our domain is 1, 2, 3, 4, 5. We do not plug any fractions into our sequence. We don't plug any decimals into our sequence. We only plug in integers. Okay? When we plug in 1, we describe that as like the first term. When we plug in 2, we describe that as the second term, so on and so forth. Okay? There are 2 types of sequences. There is a finite sequence, which has a finite number of terms. Notice how it stops at 15. And then there are infinite sequences, sequences that keep on going infinitely.
We wanted our independence and we did not want to associate with the boss. We just made it. Sure, color for you.
Okay, so we have finite sequences that stop. So how many terms are in that finite sequence I have on the board? 5, okay? But then how many terms are in the infinite sequence? Infinite, okay. There are 2 different ways we can write a sequence. The first way is what we call an explicit sequence. And the explicit sequence looks like a formula where we plug in numbers for n, most likely, to find terms. I don't like it any more than you do, but a lot of today will be defining what things are and what things mean. Okay, getting used to notation. I'll show you what we're doing. This right here is an example of an explicit sequence. It looks like, okay, well, here I say it looks like a formula, right? Instead of x, we are using n. N is going to be the variable that we use in sequences, okay, to kind of separate our minds from functions and graphing and that kind of thing. So n is the variable we are going to use. So this is an explicit sequence. Okay, it's explicit because we're going to plug numbers in for n to get that certain term. Okay, so if I want the first term, do you see this says this is a subscript? We say it a sub n. All right. So our first term we're going to write as a sub 1. And we're going to find our first term by merely plugging in 1 into our formula. So our first term is 2. Our second term means we're plugging 2 in for n. So our second term is, thank you, our third term means we're plugging 3 in for n. And our third term is, oh yeah, Gabby, what would our fourth term be? 17. We have 4 squared plus 1. And our fifth term, Connor, what is it? 26. Okay. So if we were to write the first 5 terms of the sequence, we would write 2, 5, 10, 17, 26. I have a second explicit sequence. I would like you to find the first 5 terms of this sequence and then compare your answer to someone next to you.
Understand, like, if you're in like a set right there, you can see that you're adding the next on the joint. So you just just enjoy it. It's probably easy, but still easy.
Remember to compare your first 5 terms to somebody next to you. Kanan, what do you have for your first 5 terms?
2, 7, 12, 17, 22.
Give me a thumbs up if you agree with Kanan.
Thumbs up.
Thumbs up if you agree. Okay, thank you. Any questions? All right, now, that is very straightforward. Plug in 1, that's our first term. Plug in 2, that's our second term, etc. Okay, now we are going to have to go backwards. I'm going to give you 2, 7, 12, 17, 22, and you have to figure out that our sequence is 5n minus 3. Okay, now, before we do that, I have a question for you. If our sequence has one of these 2 things attached to it, like multiplied to it, how is that going to affect our sequence? Okay, if you want to think about like -1 to the n times, what was it, 5n minus 3, or vice versa, what is that piece going to do to the terms in our sequence? You and your pod talk about it first.
-1 squared is positive 0.
Well, it's -1 here, so it's not going to do anything.
Or change the sign.
It was like
Well, -1 squared is positive.
All right, pod 6, what's going to happen? I mean 5. I'm looking at 5.
the signs are going to alternate. Like it's going to go positive, negative, positive. Negative.
Okay, they are going to alternate signs. Okay, so if you see a sequence that goes positive, negative, positive, negative, positive, negative, you know that you're going to have one of these multiplied to your rule. Okay? Now, if we have this, is the first term going to be positive or negative? Negative. -1 to the first is negative. However, if we plug 1 in here, we have -1 squared. So this would cause your first term to be positive. Okay? So when we get to one of those, we'll talk about it again. I'm just warning you that that could happen. All right? So, there are 2 different ways that I'm going to describe an explicit sequence. I'll either ask you to write the explicit sequence, or I will ask you to write the nth term. Those are going to be interchangeable if you need to make a note to yourself that nth term means explicit. Okay? So I'm going to give you a sequence, and we're going to have to figure out how to write the nth term. Okay, so write this down, and I'm going to give you like 15 seconds to discuss with your pod any patterns that you see. All right, pod 3, what's our pattern?
We're adding 4 each time.
We add 4 every time.
I mean, you can have 2 squared every time.
All right. So now we need to come up with a way to plug in 1 to n to get 1, and then plug in 2 to n to get 5. Plug in 3 to n to get 9. I mean,
4n minus 3.
can you please tell us how you came up with that?
Well, I just kind of plugged in some things. If you have to add 4 every time, then I don't know. It just works.
Okay, if it's going up by 4 every time, that's how you got your 4n, right? 4n would give you 1. 4, 8, 12, etc. Okay? So if you're going up by the same number every time, okay, you can write that number times n. But then, since we want our first term to be 1, we need 4 times 1 minus some number to get 1. So if we have 4 times 1 minus 3, we get our first term of 1. If we plug in 2, we get 4 times 2, which is 8, minus 3 is 5. 4 times 3 is 12, minus 3 is 9. This formula now works for each of our terms. Get another one. First of all, what do you notice? They are alternating. So we know that we're going to need one of those alternating pieces. Okay? So since our first term is positive and our second term is negative, do we need negative 1 to the n or negative 1 to the n plus 1? Okay, good. When we plug in 1, negative 1 squared is positive. That's how we get our first term to be positive, then second term negative. Okay? My advice to you, if it is an alternating sequence as far as sign value, figure out negative 1 to what power, what do you need, and then look at the numbers without the signs. So think about 2, 9, 28, 65, and 126. Okay? These obviously aren't multiples of some number. They aren't being multiplied by the same number over and over. I'm going to give you and your pod about a minute to brainstorm how we can get those numbers. Okay, so talk to each other, just throw out ideas. No idea is a bad idea.
Oh, you're adding 1, 8, and those are all one way. So, like, what?
Okay, who has an idea? Jackson.
An idea, like, it could be n cubed plus 1.
Okay, our perfect cubes are 1, 8, 27, 64, and 125. All of those numbers are 1 away from perfect cubes, so n cubed plus 1. There it is. Okay? Now, this is probably one of the more difficult ones. If I were to give you something like this,
Okay.
okay? If I gave you something like this, how would we write the rule? Darby?
N over n plus 1.
Okay, good. We plug in 1, we get 1/2. We plug in 2, we get 2/3. We plug in 3, we get 3/4. Okay? That would be one that I would hope that you can get. Okay? Now, remember, these are going to take some practice, so just be patient when you're doing your homework tonight. Okay? All right, so we talked about an explicit sequence. We are now going to talk about a recursive sequence. There's 2 different ways we can write a sequence. Okay? A recursive defined sequence gives you the first term and how the successive terms are related. Okay, so this is basically we're writing a term based on a previous term. And this is what it's going to look like. They're going to give you at least one term, and then the rule is going to be written based on a previous term. So go ahead and write it down, and we're going to talk through it. All right, so they have given us a sub 1. Now let's imagine finding a sub 2. Well, this means our n is 2. So this n minus 1 becomes a 1. So basically this is saying the second term is the first term plus 5. What is our first term? Negative 10. So this is really negative 10 plus 5, which is negative 5. Okay, let's go back to our rule. If I want the third term, if a sub n is a sub 3, then a sub n minus 1 means a sub 2, 1 less. Okay? So our third term is our second term plus 5. Well, we just found our second term is negative 5 plus 5 is 0. Okay, so do you see how we can only find the next term if we have the one before it? Okay, I can't find the 20th term without the 19th term. That was not the case 2 slides previous. Okay, we wanted the fourth term. Okay, a sub n equals a sub n minus 1 plus 5. So our fourth term equals our third term plus 5. We just found our third term. It is 0 plus 5 is 5. And from that point, yes, you can. So our sequence is negative 10, negative 5, 0, 5. It keeps going. Right? Okay, what I ask that you do is go ahead and write down this example 6. And then as you come back from lunch, I'd like you to start working on it. So when you have it written down, you may Okay, so you started working on this example 6, okay? They have given you the first term and the second term, and then our recursive definition looks a little different. They had to give you 2 terms because this sequence is based on the 2 previous terms. So we have the first, we have the second. If we go to find the third term, n is 3, which means n minus 1 would be,
2.
and n minus 2 would be 1. So our third term is the second term plus the first term. Second term is 2, first term is 1. Our fourth term, if n is 4, that means n minus 1 is 3, and n plus 2 is 2. So our fourth term is the third term plus the second term, which would be 3 plus 2, which is 5. And then the fifth term would be the fourth term plus the third term, which is 8. So we have 1, 2, 3, 5, 8. Those would be the first 5 terms of the sequence. Will, did you have a question? You sure?
Yeah.
Questions on the recursive? What did we skip the first one? Oh, are you thinking it's like Fibonacci? Okay, if this were the Fibonacci sequence, it would be 1, 1, 2, 3, 5. Did you do Fibonacci stuff last year?
Yeah.
Okay, that's what I thought. All right, so the Fibonacci sequence is a recursive sequence. This is almost it, but not quite. Good job for catching that. Okay. All right, let's talk about a series. A series is the sum of a sequence. Okay. Sum means what? Addition. Okay. And this is where we get some fun symbols. Right, Henry? This is called a sigma. It means sum it up. Okay, this is I equals 1, this is A sub I, and this is N. Okay, what do all of these things mean? I is the index, it tells you where to start. So if that says I equals 1, you begin by plugging in 1. If it says I equals 3, you begin by plugging in 3. N is the upper limit, that is where you stop. So if that N is a 6, and I equals 1 down below, you plug in 1, then 2, then 3, then 4, then 5, then 6, and then stop. Okay. 1 then is the lower limit. Okay, so the lower limit, upper limit tells you where to start and stop. Okay, you're going to find each term of the sequence beginning with the lower limit, stopping at the upper limit, and then add them together. Okay, the most fun part about this is drawing a little sigma. Okay, yes.
So do only recursive sequences have the upper? So if you just had explicit sequence, would you not need
Actually, it has to be written explicitly to be able to use the sigma notation. Okay, and I'll show you what I mean here in a second. Okay. Here is the first sum that we are going to take. Okay, so it has to be written explicitly so we can plug that value in. Okay, now here I'm using I. You could see N being used. You could see K. It's usually not going to be X. X we kind of save for functions. But just so you know, it's not always going to be the letter N. Okay? So what does this mean right here? We are going to begin at what number? 1, and we are going to stop at 5. So we are going to plug in 1, and then plug in 2, and then plug in 3, and then plug in 4, and then plug in 5. 3i plus 3i plus 3i. And then we get to add those together. What is 15 plus 12 plus 9 plus 6 plus 3? 45. After tomorrow, you will know a trick to do that faster. This is true. I'll show you
Cooler trick. Oh man, I'm excited.
It is a cool trick. It is a cool trick. I'm proud of you for saying that. All right. This is one that I'd like you to do in your notes and then compare your answer to a neighbor.
Draw a signal correctly.
Just so that, like, that is the set.
When you have your sum, compare it to a neighbor.
I got double the last one.
Okay.
What'd you have?
Hannah, what did you get?
90.
90. Give me a thumbs up or a thumbs down. Do you agree with Hannah? 90. Okay. Thank you for your thumbs. Since the lower limit is 3, we start by plugging in 3. Then we plug in 4, then we plug in 5, then we plug in 6 and stop because 6 is our upper limit. Ah. Okay. Gabe, I'm glad you made that mistake. Gabe said, oh, I did 6 terms. Okay? This is not the number of terms. This is the number that you stop plugging in. Okay? All right. I am going to show you some properties of sums. I don't think that it's necessary that you write these down, but if you want to just write that they're on page 610, let's talk about them, and if you need to look them up, then you can. Okay, so this is on page 610, and I think some of these are obvious. Okay, if we have the sum of just a constant, so like the sum of 5, okay, then that means you have 5 plus 5 plus 5 plus 5 plus 5, right? So if you have the sum of a constant, you're just going to multiply that constant by how many times you're adding it up. Seems reasonable, right? Okay, this means right here, if you have a constant multiplied to your rule, you can either keep it in the sum or you can move it outside of the sum. That means that over here, we could have just added up 1 plus 2 plus 3 plus 4 plus 5 and then multiplied by 3. okay? And then these two are basically saying if you have a sum or difference inside of your summation, you can break those apart into two separate summations. Okay. Is everyone okay with those? I don't think it's necessary to write them down, but if you want to reference them, and you can come back to it later and write them in your notes if you really feel like you need to. Okay. All right, a little bit of terminology about these sums. Now, I talked about how we have finite and infinite sequences, correct? We have the same thing with sums. Okay? And remember, sums are also called series. Okay? So, let's imagine that we have an infinite sequence. I wouldn't write that down. This is called the nth partial sum or a finite series, okay? Where we have a sum that stops. And since it stops on the nth term, whatever that n is, it is the nth partial sum. So if I say the fifth partial sum, the last term that you're adding is the fifth term. Okay? And we call that a finite series because it's a series that stops. Okay? Remember, series and summation are one and the same. Let's see. On a side note, before I finishing, Dirty Nothing, right there is yours. His parents have a restaurant in Kansas. They ate it this weekend.
It's almost like you're famous.
They had a Christmas tree, and on the top of the Christmas tree was a cheesehead.
I have cheese.
Okay. The sum of all the terms in an infinite sequence is called an infinite series, where we just keep adding and adding and adding and adding and adding and adding. Yes.
These things do that.
Well, we will have numbers. And here's the thing about an infinite series. There are times where an infinite series does not add up to anything. It just keeps getting bigger and bigger and bigger and bigger and bigger. Okay, it just adds up to infinity. There are special times where it actually, what we say, converges to a number. It gets so close to a number, we say that the sum is that number. And we'll work with this a little bit today and a lot more on Wednesday. Okay, so you'll see what I mean here on the next slide with how we can actually find the sums. Not always can we have a value to the infinite sum, but there are times that we can. So let's look at that. Okay, notice how here we have from 1 to infinity, where up here we'll actually have a number right there. Okay, go ahead and write this down. Third partial sum means we're going to add up which term? First three. So our first term plus our second term plus our third term. Okay. Now let's think about what this is. 3 over 10 is 0.3. 3 over 100 is 3 100s. 3 over 1,000 is 3 1,000s. So what's our sum?
3.
Or 333 over 1,000 if you keep it as a fraction. Okay? Now, I wrote it like this for a reason. Here, we're going to find this sum. What kind of sum is this? Infinite. Okay? But Mrs. Holman, how can we find an infinite sum? Okay? Watch what happens. We have 3 tenths, 3 100ths, 3 1,000ths, 3 10,000ths, 3 100,000ths. Are you getting my drift here? Okay. Okay, I'm running out of room. What's happening?
1/3. That's happening.
1/3.
We have 0.3 repeating, right? As the more terms we add, we're just going to get another 3, 3, 3, 3, 3, which is 1/3. So this infinite sum actually is a number, 1/3. Isn't that cool? That's so cool.
Yeah.
What? Makes you kind of sad? Okay, now, if we had the sum we had this sum right here. 3 plus 6 plus 9 plus 12 plus 15 plus 18. Is that going to add up to be anything? That's going to add up to be infinity, right? But there's a special case where we can actually get a value out of that. And like I said, we'll talk about that a little bit more.
Sum of I. Like, what gives you class? Like, what's the equation that will make all of
Pi?
Divided by 2 times 3.
Well, yeah, but like, what is, like, so like that way, you wrote it like 1/3, so like, the 3 over whatever. But what if you, but like, since pi is also like an irrational, like, forever number,
Uh-huh.
what's the sequence?
I'm not sure if there is one, but I know that there is a series that gives you the letter E, or excuse me, the number E. So let me wrap this up and then I'll write that on the board for you. Okay? That's a great question. Okay? I do want to come back. We've kind of talked about factorials already, but I want to go through simplifying because you'll have some in your homework. Okay, we know that n factorial means 1 times 2 times 3 times 4 times 5 times 6, all the way up until you get to n, right? So we're going to simplify 2 expressions. This is the first. Okay. What does 8 factorial mean?
7 times 6.
Right? Now, to save some time, what could I write this as right here? Okay, I'm going to go ahead and do that then. So that down here I can write 2 factorial is 2 times 1, and then times 6 factorial. I did that so we can just cancel these out. And this reduces to what? Excellent.
It'd be so much harder. It's like an English.
Last one. N plus 1 factorial means what?
N plus 1 times n, that's n minus 1. Or you could just say n factorial.
Right, all the way down. Okay, or could you just say n factorial? And then what can happen? Okay, so your gold sheet is going to have the homework for tonight's assignment. Hold on, I'm trying to get this formula for you here. Okay. Please be patient as you're doing your homework. I know right now everything seems kind of random, right? And I haven't really given you like a one-way method to do each type of problem. Okay, especially the ones where you have to write your own rule. Tomorrow and Wednesday, when we focus on the two different types, the main types of sequence, you'll see like some better patterns and whatnot. Okay. This is the number E.
But then there has to be one for pilot, right?
I'm gonna have to look that up.